All right, good morning, 020. Today is the last lecture of technical content of the semester. So that's kind of exciting. And it's the last time we're going to use this little piece of graph paper, which is not particularly exciting. But anyway, next week we're going to change gears a little bit and do our second social and personal hour on Monday. And I'll send around reading for that shortly. And on Wednesday, we're going to do a Zoom game show. So I hope we have a good attendance for that, because we're going to try to make it as fun as we can over Zoom. It won't be as much fun as in person, but still. Anyway, that's next week. Today, we're going to work an example, which pulls together some concepts which we've been using the last couple lectures. So this is what we're going to work on today. Reacting systems that have gases and condensed phases. So, we spent a couple lectures in the middle of the term on reacting systems with just gases. And then in the last couple lectures, we've talked about oxidation, which are reacting systems with oxygen gas and condensed phases, that is metals and oxides. So we're going to just generalize that a little bit. I shouldn't say generalize, because we're going to work a specific example. We're going to move away from oxides and do an example problem, which I really think ties together a lot of concepts. And it's a silicon carbide problem. And before I move in here, this is not, everything we're going to do today is not necessarily particular to silicon carbide. It's particular to silicon carbide in the details, of course, but the approach is general for a lot of materials. So what I'm going to do is show you the phase diagram of silicon carbide and briefly talk about why anyone would care about silicon carbide, and then we'll start working on the problem. So let's see, here we go. The formation of silicon carbide. Okay, before I label the solid phases, how many solid phases are there in this diagram? You should be able to read a diagram like this by now. Three solid phases. Silicon is a line compound here, which is, I've sort of given you a hint, silicon carbide. So silicon, silicon carbide, and carbon, right? So three solid phases, thank you, and one liquid phase. And all right, so here's a paratectic reaction, right? This is a paratectic reaction. Has a T shaped. It's a liquid silicon carbon containing melt and graphite reacting to form silicon carbide. So silicon carbide forms out of a paratectic. Silicon, of course, melts at 1414C. Carbon doesn't melt, actually, it sublimes, and it's way off the scale. It's like 4,000 degrees or something like that. And silicon carbide decomposes. It doesn't melt, it decomposes at very high temperature. So you can see the silicon carbide here is a refractory material. It's a refractory ceramic material. So it's a very hard, it's corundum. That's the mineral. It's also known as moissanite. So it is a wide band gap semiconductor and an abrasive. And I learned a couple things about it. I knew it's an abrasive. A lot of times if you go and buy grinding wheels and such, or high performance mechanical abrasives, or ultra hard components used for brake pads and things like that, it'll be silicon carbide containing. That I knew. Silicon carbide is a wide bandgap semiconductor, and it may be the future of power electronics. So that it's important in my area of expertise for that reason. I also learned today that it was the first ever LED was made with silicon carbide. It's about 110 years ago. And it was noticed that silicon carbide can be made into an LED. Of course, it's not the LED wide bandgap material of choice. Does anyone know what wide bandgap semiconductor is providing most of the light, quite possibly in the room you're sitting right now? Nobody knows. It's a Nobel Prize a couple of years ago, gallium nitride. So another wide bandgap compound semiconductor, not a refractory material. It falls apart more easily than silicon carbide. But anyway, there's lots of exciting reasons to know you should know about silicon carbide. And I think you should care about it too, because it's important for a number of reasons, and it's got an interesting history. Enough about that. Let's talk about a problem. So I'm going to give you a problem. This is like a word problem you might find on a test or something like that. Place pieces of silicon carbide and carbon, and for now I'll label that graphite, but you just keep in mind it's carbon, right? Into a vacuum oven. The vacuum oven is an oven that can operate under vacuum, right? They're all over campus, if you don't know already. And now I'm going to do it. I'm going to put them in the oven, and I'm going to pull vacuum. That means evacuate the oven. And we're going to pull this vacuum to approximately 0 pascals. So, there's no absolute vacuum, but on this scale, your gauge is reading 0. Okay. We're going to seal it. Pull vacuum, seal, and then heat. To 1700 C. Okay. You observe two things. Silicon carbide and carbon are both still present. You also observe that the pressure is 4.0 pascals. So let me draw this visualization here of the experiment and what you observe. It's a vacuum oven. It's got a nice insulated walls, nice vacuum seal. A lot of money for a vacuum furnace that can go to 1700 C, but there's a number of them on campus. And okay, so here's silicon carbide. It's a chunk of silicon carbide sitting there in the vacuum furnace. And a chunk of graphite should be gray, right? Why not? Graphite, a chunk of graphite. Okay. And you've got some gauges on there. Often gauges and block diagrams are indicated like that. So you've got a gauge saying that pressure equals 4.0 pascal. And you've got another gauge reading the temperature equals 1700 degrees C. Right. This is the problem statement. Are there any questions about the problem statement? I haven't asked the question yet. This is a setup. Would somebody express this observation in thermodynamics language for me? What does this observation mean?
There are multiple phases.
Right. And the phases are?
Silicon carbide and carbon.
Oh, right. I'm sorry. That's not, yes, that's right. The phases are in? Someone just whispered.
Equilibrium?
Equilibrium, right? The phases are in equilibrium. You heat it up and you observe that they're present. This is a class in equilibrium thermodynamics. So right, you can infer from context that these things are both present, so they are coexisting in equilibrium, right? Multiple condensed phases coexisting in equilibrium. What's the third phase that's present? You can't see it. This is important. You need to be able to interpret these observations in thermodynamics language, right? And if you're going to solve thermodynamics problems. So We've got two condensed phases in equilibrium. There's a third phase. Would somebody tell me what is the third phase?
Gas phase.
Gas, right? There's gas. There's a gas phase there. You can't see it with your eyes, but it's there. Your pressure gauge tells you it's there, right? There's some pressure. There's some gas pressure. Good. Thank you. All right. Here's a question. What is the Gibbs free energy of formation of silicon carbide at 1700 degrees C? That is silicon in its solid phase plus carbon in its graphite phase going to silicon carbide. And I'm asking for delta formation. And I'm going to give you some reference data. You need a little bit more information to answer that question. Reference data. You know or you measure that the saturation vapor pressures at 1700 degrees C are, this is the data you have, P silicon saturation 1700 degrees C equals 4.4 pascals, and P carbon saturation at 1700 degrees C. What do you think it is? Is it larger than silicon or is it smaller than silicon? The saturation vapor pressure of carbon. You might ask yourself, which is more volatile? I'll give you a hint. What are the saturation vapor pressures of these refractory materials? Are they higher than that of silicon, or are they lower than that of silicon? Think about what you know about bonding. Think about what you know about refractory materials. Ask yourselves, what's more volatile?
So would the saturation vapor pressure of carbon be 0 then?
The saturation vapor pressure of nothing, there's no component or compound for which the saturation vapor pressure is 0, right? Think back to the unary phase diagrams. It's always finite. It's something, right? It exists. But how does it compare to that of silicon?
It would be much smaller.
Much smaller, right? Exactly. Much, much less than P sat of silicon. That's right. Because these are, and this should be something that you just sort of intuitively understand, which is that more strongly bound compounds, refractory compounds, are less volatile and therefore have lower vapor pressures. They also have lower melting points, right? You know that, carbon is very strongly covalently bonded to itself. Silicon is strongly, but less so, covalently bonded to itself. Germanium is even more volatile. It falls apart more easily. And by the time you get to tin and lead, you have really high vapor pressure, low melting point materials. So, right, there's some sort of periodic table knowledge there. All right, both of these are about below 10 to the minus 5 Pascal. So you have these two materials that have very, very low saturation vapor pressure. and one that has a reasonable saturation vapor pressure. That's the reference data. Okay, here's the problem statement. What is the Gibbs free energy of formation of silicon carbide? So what I'm going to do is I'm going to start by, I'm not going to start by asking how do you solve this problem. I'm going to start just by writing down an expression for the thing we want to solve for. Just manipulating terms, trying to think out loud here on the page. So let's see. Delta formation of silicon carbide. Well, just by definition, right? I know what that is. It's the Gibbs free energy of silicon carbide minus the Gibbs free energy of silicon in its reference state, in its pure state, minus the Gibbs free energy of carbon in its reference state. Right? Because it's, and the stoichiometry is really easy, right? 1 mole of silicon and 1 mole of carbon forms 1 mole of silicon carbide. So, this expression is very, very easy. All right. Well, for 1 mole of silicon carbide, G silicon carbide equals this is just partial molar properties. So this we know. And it's just the chemical potential of silicon plus the chemical potential of carbon, right? This we know. In silicon carbide. In silicon carbide. So it's just partial molar properties, the stuff we know. And I'm just going to plug this in, and what we get is the free energy of formation of silicon carbide expressed in terms of the chemical potentials. So it's the chemical potential of silicon and silicon carbide plus the chemical potential of carbon in silicon carbide minus the chemical potential of silicon in its reference state minus the chemical potential of carbon in its reference state. I'm going to do one more thing. I'm just going to rearrange. I'm going to see it's silicon in silicon carbide minus silicon in its reference state and chemical potential of carbon in silicon carbide minus chemical potential of carbon in its reference state. So I have the free energy of formation expressed in terms of differences in chemical potential. And you can see how this is similar to solution modeling, right? I have delta mu's. This is a delta mu. This is a delta mu. It's just the stoichiometry is fixed, and so we don't have to worry about composition variables anymore. We just have one of these and one of these. All right, and I'm gonna tackle these one at a time. So I'm gonna tackle this one first. So I'll just label it 1, and I'm gonna tackle this one second. I'm gonna label it 2. So if we can find equations for these quantities, right? Then we know our answer. So I'm going to take these one at a time, and then I'm going to start asking you folks some questions. So look alert. Let's take one first. 1. What I want to do, sorry. One of the things I want to do with this working an example thing is I want to flip back and forth between equations and word problems and equations. Right? That you have to be nimble and you have to know the material well enough to do that. You know by now that's an important skill. So how does the chemical potential of carbon differ from its pure reference state? Right. This sentence is this expression, right? This expression is the difference in chemical potential for carbon in between this compound and its reference state. That's what that expresses, right? That's also what this expresses, right? How does the chemical potential of carbon differ from its pure reference state? So I'll ask you, somebody please, Volunteer an answer. How does the chemical potential of carbon differ from its pure reference state? And while you're thinking about that, I will just return to my observation.
So I guess this is kind of like the piece set, right, where they're in equilibrium. It's in equilibrium with the pure phase.
Okay,
so
good.
it should be
And so your answer is
it should be the same.
right. Right.
Oh, yeah. Sorry.
It doesn't. It doesn't. It doesn't differ. Why? Pure carbon is in equilibrium with silicon carbide. That's an observation. What that means is that chemical potential of carbon in silicon carbide is the same as the chemical potential of carbon in that graphite phase, which is sitting there, which is by definition the chemical potential of carbon in its reference state. Good. And let me remind you why that is. Because this is, the type of thing we've been doing all semester is thinking about the conditions for equilibrium, the criteria for equilibrium, if you like. Here's graphite, there's silicon carbide. Well, there's a gas phase too, right? The carbon atoms are exchanging. I'm going to draw some carbon atoms in the gas. The carbon atoms are exchanging freely, right? That's an unconstrained internal process. They're exchanging freely between silicon carbide and carbon, well, graphite, via vapor phase, via the vapor phase. When we had conservation of mass with mass exchange between two phases, that led to the condition for chemical equilibrium, right? Chemical equilibrium. Right, that was about the middle of the term that we arrived at that. So chemical equilibrium, right? That's what I wrote down here. Okay, so that's great. That means that what is this term equal to? What is the term in the expression in the parentheses equal to?
Zero.
Zero, right? Exactly. There's no difference in chemical potential for carbon between the compound and the pure state, right? Thank you, Ian. Okay, great. So half the right-hand side of the equation is put to bed. Let's put the other half of the right-hand side to bed. Let's take care of part 2, which is right, expressing in words. Part 2 is the difference in chemical potential for silicon between the compound and its pure state. So I'll write that out in words. How does the chemical potential of silicon differ from its pure reference state? Okay, so that's what that, okay. So this is a little harder. I'll walk you through this. Are there any initial thoughts on how to go at this? Anyone want to take a gamble? Let me give you a hint. Okay, if solid silicon, or I should say liquid, because we're above the melting point, condensed. I said solid in the lecture notes, so that's a typo. If condensed silicon were present, the partial pressure P silicon would be equal to what would the partial pressure of silicon be equal to if condensed silicon were present? If condensed silicon were present, what would the partial pressure of silicon equal to?
The saturation value.
Right, thank you. Okay. So that's a hypothetical because there's no condensed silicon there, but it's a starting point. If condensed silicon, okay. So therefore, chemical potential of silicon minus chemical potential of silicon in its reference state equals. This is a bit of a kind of an aha thing. You have to see the connection here between different parts of the semester. The chemical potential of silicon in this system relative to what it would be if condensed silicon were present. If condensed silicon were present, the chemical potential would be equal to its reference state chemical potential. Also, if condensed silicon were present, the pressure would be equal to the saturation pressure. Okay, I'll just give it. Therefore, the chemical potential difference of silicon relative to the reference state is RT log P silicon over P silicon sat. Why is this? This is recognizing that silicon in silicon carbide is in equilibrium with silicon in the gas phase. Right? Here's another, you have to imagine this, silicon carbide, right? And there's silicon vapor. You can't see it, but it's there. And you know that the silicon vapor is in equilibrium with the silicon carbide. Those components are in equilibrium because they can freely exchange. So they're in chemical equilibrium. So whatever the chemical potential of this vapor phase is, it's the same as the chemical potential of silicon in this compound. And you know how to calculate the chemical potential of a vapor phase. It's RT log partial pressure over the reference partial pressure. Okay. That was cool. We're not done yet. What is partial pressure of silicon? I'll remind you, the total pressure now equals 4.0 pascals. The total pressure equals 4 pascals, right? Gas phase. What are the gas phase components? What sort of molecules am I finding in the gas phase? Told you I have silicon. What else is there?
Silicon. Oh.
Yep. Thanks for that. What else?
Probably nitrogen, oxygen if it's like from the general air.
No, because we pulled vacuum before we did this. That was a key thing. So there's nothing in there except what we put in there, which was silicon and silicon carbon and silicon carbide. So what other components are in the gas in general? What else could be there?
Carbon gas?
Sorry?
Carbon?
Yeah, there's carbon. And we could allow that there's maybe some silicon carbide molecules. Turns out it doesn't matter whether they're silicon carbide molecules, right? We know that carbon and silicon carbide are saturated, right? We know they're saturated. That's just by observation, right? Because the pure components are there. So their vapor pressures are saturated. They're saturated, but their saturation vapor pressures they're negligible because they're refractory materials. We talked about that 20 minutes ago. Okay, so what does that mean? Somebody?
Sorry, I have
that
a
mean?
quick question, if that's all right.
Yeah, go ahead, please.
Earlier, I think we talked about how the carbon wouldn't vaporize nearly as much as the silicon. So would it make sense to ignore it in future calculations, or do we still need to take it into account, even though it's less likely to vaporize?
So Sarah, your question is exactly my question, which is this. So what is the silicon partial pressure? And if it's not clear right now why your question is my question, I'll make that clear. But somebody, please, here's your observations and some facts and things that you know. Would somebody make a guess for the silicon partial pressure?
It's just equal to the total pressure.
Thank you. Yes, that's exactly right. The silicon partial pressure is basically the same as the total pressure. In other words, the vapor is essentially pure silicon. That's the second kind of big intellectual connection which you need to make to solve this problem. The first was the change in chemical potential for gases when they're rarefied. The second is, well, it's sort of a more pragmatic thing, right? You have all these things in the gas phase, but I know that the pressure of carbon and silicon carbide is really small, unmeasurable on my gauge, right? Definitely not making a contribution to that 4.0 pascals, maybe at like the 6th decimal point or something, but who cares, right? It's 4.0 pascals. So my gauge only has 2 digits of precision anyway. So I can infer that that pressure is totally silicon. Right. So now I plug and I chug. The chemical potential of silicon in this system minus the chemical potential of silicon for condensed pure silicon, which is RT log P silicon sat, is just RT log 4.0 over 4.4. So I'm putting it all together. Therefore, delta formation G of silicon carbide, it's 2 terms, chemical potential of silicon minus chemical potential of silicon in its reference state, and the chemical potential of carbon minus chemical potential of carbon in its reference state. And that's 0. And this is RT log 4.0 over 4.4, which happens to equal to minus 1,563 joules per mole. That's the answer. So I intentionally left a good amount of time to talk about this problem, but I want to start with sort of a strategy for solving these types of problems and to solving all thermal problems, actually. The key to solving such problems this is sort of the intellectual key, is to ask who is in equilibrium with whom? This is the key to getting good at these problems. What do I mean by that? Let's see, we have vapor, carbon, silicon, silicon carbide. We have condensed silicon carbide. We have condensed graphite. And the components are freely exchanging, right? So this here, we have these components freely exchanging, right? Exchanging mass. Back to the basics, right? Back when we developed chemical equilibrium. As opposed to, right? Vapor, silicon, imagine silicon carbide, silicon carbide, okay? Those are in equilibrium. But what about solid silicon? Right. Not in equilibrium. Not in equilibrium. Not in equilibrium with condensed silicon. What does that mean? It means that the vapor pressure is below saturation. Because when I saturate the vapor pressure of a thing, that thing starts condensing, right? It starts condensing out of the air. It starts raining silicon, right? If the vapor pressure reached the saturation vapor pressure of silicon, it would start raining silicon in that system. But that didn't happen. So the vapor pressure is below. Okay, so that was a lot of stuff, all wrapped up into one problem. It's good that I have 10 minutes to talk about it. So I'm happy to take questions about this or anything else. I will mention one last thing on course scheduling. Wednesdays, office hours, I'm planning to do a really informal kind of semester in review. So hopefully that'll be useful. But back to this problem. Questions, confusion?
I had a question about something very early on.
Mhm.
So how is it that we knew that the vapor pressure of carbon was a lot less than silicon? Was that reading from the graph or?
No. So that was not, so there's two things. First of all, I gave you reference data. So that was like data given with the problem. So one way is that it was just in the problem statement, right? So you say, it's fine. But it is worth asking yourself, would you have been able to infer that if that hadn't been given in the problem? And yeah, you might guess that. You might know that silicon carbide and graphite are refractory materials, right? You might know that they're very tightly bound molecular solids with a huge cohesion energy. It's very hard to break them up. And the phase diagram here tells you that silicon is a lot more volatile than either silicon carbide or carbon. It's got a much lower melting point, right? So you might just guess, and I wouldn't ask you to do that, but you might be able to infer that the saturation vapor pressure of silicon carbide and carbon is very low. And if you remember, the saturation vapor pressure, it's proportional to e to the minus delta H of formation. You remember that from unitary phase diagram. So a material that has a very large energy of formation has a very small saturation vapor pressure. So maybe you know that silicon carbide and carbon are very happily bonded solids. again, I wouldn't ask you to necessarily come up with that in the context of a big problem like this, but it could be done. It would be an educated guess. Does that help?
Yeah, that helps a lot. Thanks.
Yeah. I mean, you know, they're volatile compounds are compounds that you can smell, right? So you can't smell silicon. You can't, I mean, maybe a dog can, but dog noses are amazing, but you can't smell silicon. You can't smell these things. And the amount that you could smell something corresponds to its volatility, right? You know this when you're dealing with solvents and paint solvents and stuff. Very volatile compounds are very smelly compounds because they have a large vapor pressure. They're just in the air. So, you know, things like that. Can dogs smell silicon? That is the question that everyone is dying to know. All right, what else? What else? No other questions? Well, maybe that was clear. All right. If there are no other questions, we can get out 6 minutes early. All right, well, thank you. I will see everyone on Monday. And again, homework due Sunday at 8 p.m.